So now we're going to go ahead and graph these data points, this data with Reynolds numbers on the X, Schmidt number on the Y, and the Sherwood number for the Z, so we can get a 3D scatter plot. And then we're also going to add a mesh grid to that. So we need a graph. So we're going to start, we need to import some more tools for graphing. So from Plotly, subplots, we're going to import the function make subplots. Yeah, that. Okay, so that'll allow us to create these subplots that we need. So we also need to import plot the graph objects, because we're going to be adding scatter plots and lines to these graphs. So we need graph underscore objects, and then we want to do as geo, just the simple, not global, as geo. So it's shorthand for that. And then we also want to import, and this is just for preference, but most of the time I like my backgrounds and everything dark, like on my phone and on Google Collaboratory as well. So we want to import plotly.io as a PO, and then immediately use the PO. That's not Plotly. I haven't been spelling right for a while. And then use templates from PO directory, and change the default setting in these templates to Plotly dark. So essentially it's making a dark mode. So let's go ahead and Plotly underscore dark. So that should create black in our dark background, and I think that's everything we need. So let's go ahead and shift enter. Okay, so it looks like we're good. Now we're going to go ahead and go down and start creating the data points, the graph, and eventually the mesh grid that goes over it. So now we're on to our final part, which is graphing this data. So we want to take the functions that we've come from before, the relationship between the Reynolds, Schmidt, and Sherwood number, and we want to graph that on a scatter plot, and then we want to add a mesh grid over the top of that best fits that data. So let's start with defining a function. Let's call it figure, and we'll say it's equal to make underscore subplots. So now we're creating the subplot for our data to go on to. So now we want to add trace. So fig, we want to add the some kind of trace. In this case, it's going to be a 3D scatter plot in terms of markers, because we want to add a marker to every single point, data point on that graph. So add trace. Oops. And then we're going to make that, it's going to be a graph object, because scatter is a graphed object. And then 3D, make sure the D is lowercase, otherwise it won't work. And we'll say X is equal to, the X-axis Reynolds number, the Y-axis gets the Schmidt number, and the Z-axis gets the Sherwood number. There's a couple other things that we can do. We want the mode set to, like I said, markers. And we're going to increase the marker size just a little bit so they're easier to see. And so each data point will have a marker. So let's go ahead and shift enter. See if this gives us our graph. So this is our, let me scroll up. This is our initial graph of our 100 points, X, Y, and Z, with Reynolds, Schmidt, and Sherwood number. So now we want to create the mesh grid. So the mesh grid is going to be overlapping layers of lines. So these lines need to have two things. So the lines going, let's say, left to right and then back and forward. So they overlap like a grid like that. So let's just say one of these set of lines is going to need to have Schmidt numbers that are constant while we change the Reynolds number, and the other group of lines is going to have the Reynolds numbers constant while we change the Schmidt numbers. So we're going to use the mesh grid function in NumPy to start creating the mesh grid. And like I said, we need to create these lines, right? And so we're going to use linspace, which evenly spaces out these lines. And then we're going to start with the Reynolds numbers, which is 2,000 to 35,000. And then we want 25 25 evenly spaced lines throughout. And then we're going to do the same thing for the Schmidt numbers. And the Schmidt numbers are valid from 0.6 to 2.5. And we want 25 lines evenly spaced out too. So Shift Enter. So we should get groups like we do here. This is the Schmidt number, so the Schmidt numbers are staying the same. So it's 25 values of 0.6, followed by 25 values of 0.679, and so on until we reach the 2.5 evenly spaced out, so the 25 lines. And then there's another group of arrays that has alternating Reynolds numbers. So each of these Reynolds numbers needs to correspond to a constant Schmidt number. And so eventually we're going to use a zip function to tie each of these constant Reynolds numbers to a changing Schmidt number and constant Schmidt numbers to changing Reynolds numbers. But for now, we're just going to call out these new variables that we've created, these new arrays, and we're going to say the Reynolds grid and the Schmidt grid are equal to those mesh grids. So now we'll Shift Enter and get rid of those arrays. We've stored them in those Reynolds and Schmidt variables now. So now we need to create the Sherwood grid. The Sherwood grid is equal to, and then we're going to use the linear regression model with the matrix manipulation. So, which is up here again, B. B is the matrix that holds our coefficients for A, B, and C. And if you remember, the first value is the natural log of A. So we need to remember to exponentiate that function, which is the first element in the B matrix, or coefficient A. And then we need to recreate that equation one more time, where it's A times Reynolds number to the B, Schmidt number to the C, where those A, B, and C coefficients are stored in our B unknown matrix. So NumPy exponential of the first element of B times Reynolds number to the not 0.83, we just want our value, not the error value. B1 times the Schmidt number raised to C, which is B2. So now that we have our grids, like I said, we want to zip up those grids so that we can correlate those arrays to actual lines, and the changing Schmidt number for constant Reynolds numbers, and vice versa. So what we want to do is, for I, J, and K, we're defining new variables in using the zip function. We want to say I is the Reynolds grid, J is the Schmidt grid, and Z would then be the Sherwood grid, colon, because it's a function. And then we want to add traces to each of these grids. So we're just going to save some time and copy and paste this code here, except X is now the Reynolds grid, so it's I, Y is the Schmidt grid, which is J, and the Z is the Sherwood grid, which is K. And we don't want markers anymore, we want lines because we're creating the mesh grid. And then we're going to, instead of marker size, we're going to change our line color. And I like gray, so we're going to go gray. So let's go ahead and see what that does. Okay, so we're getting an error. Let's see if we can't find out what this error is. It says, receive harmony, Z. Okay. Oh. X, Y, Z is I, J, K. Ooh. These should be, yeah, we want the grids here because we want this times every value, not just one. That's probably where I went wrong. Let's try this again. Okay, so that looked like it works. So let's go ahead and see what our new figure looks like. we should have lines going across, and we do, which is good news. So now we have lines going across. We have 25 evenly spaced lines that go across. So if we go back up here, we remember that our for these lines, we have the Schmidt number staying constant and the Reynolds number changing for each constant value of the Schmidt number from 0.6 to 2.5. What we want to do is simply copy and paste that same exact code and create a mesh by going the other way. So essentially flipping our variables creates the mesh where the Reynolds numbers are constant for each changing value of the Schmidt number. And the only thing we really have to do is change the order of our linspace. So there we go. So this should add the second values to the graph. So creating essentially the mesh, the two layers of grids. So let's go ahead and see. Yep, and it looks like that worked as well. So now we have a mesh grid between all these data points. The 100 data points that we originally had from our linear regression model are between now this mesh grid where the Sherwood and Schmidt, or the Reynolds and Schmidt numbers are overlapping each other, with one staying constant and one changing, and vice versa. So now that we have that, we have kind of like a little maintenance that we can do in how our graph looks, because it's essentially done. We just have to add this legend. Can be kind of annoying, as well as we have X, Y, and Z instead of their respective names. So let's go ahead and add this last line here to make it look a little bit better. So we're going to figure, we're going to update layout. And then to update layout, we're going to change a couple things. We're going to change the width equal to 800. The height, we're also going to change equal to 800, so it's more of like cube. And then we're also going to update thing called show legend equal to false, which means it's not going to display. And then we also want to scene predict. And then we're going to enter our new axis titles. So the x-axis underscore title is going to be equal to, and then the x-axis is the Reynolds number. And then we're going to do this 2 more times for the Schmidt number and Sherwood number axes. Y-axis title is now the Schmidt number, and the Z-axis title is now equal to the Sherwood number, excuse me. So let's go ahead and shift enter that and see if we get what we want. Okay, so there we go. So now we have our graph with no annoying legend and the points from our data. So this again is for our linear regression model that involved matrix manipulation, and then we added a mesh. Excuse me, I've been talking a while. We added a mesh grid on top of our 100 data points that best fit that based on a linear regression model. So we have our 100 points listed out in blue, as well as the mesh grid that overlaps these. And again, like I said, the mesh grid was formed by creating those equally spaced out lines between the Schmidt and Reynolds numbers, where one was held constant and one was changing, and then we zipped those together to create the mesh grid. So this is essentially what the final looks like for this problem. So yeah, I always think it's really cool looking at 3D scatter plots in Python. And Excel has been ruined forever. So thank you, Carlos, but I think this is really cool.